Assalamu alaikum warahmatullahi wabarakatuh. Good evening, dear students. Today, once again, Mr. Sadiq is there in front of you. You can see some of the dancing molecules in front of you. The names are written there like tetrahedral, trigonal planar, octahedral, square planar. All these names are written there. It's a very fascinating topic, actually. We are going to study about the shapes of the molecules. And which concept are we studying? The concept is called VSEPR, Valence Shell Electron Pair Repulsion Concept. It's a fascinating concept, actually. I want to make easy the concept for the students, those who are new to the concept and those who are still working on it. So stay tuned to the channel, keep watching. I'll be explaining this concept in the coming slide. So be very okay, dear students. VSEPR concept, we are working on that. VSEPR, okay. And according to this concept, we are having a central atom represented by A, which is surrounded by another different kinds of atoms, can be 1, 2, 3, 4. So I'm just focusing on anti, and number of electrons are represented by E. So this is the central atom, okay, central geometry of the molecule will be moving around this. This is the surrounding atom, okay, and here are the electron pairs. Electron pairs, okay. Now VSEPR is valence shell electron pair repulsion concept, okay. So it's the repulsion concept. This concept only talk about the repulsion of an element. So according to this concept, there are two types of pair of electrons around the central atom, okay. One is called two types of pairs, two types of electron pairs, which are number one, the lone pair, and lone pair can be represented by two dots or two crosses, okay, or bonded pairs, which can be represented by either a cross and a dot or a dot and a cross, right? So according to this concept, bonded lone pair and lone pair occupies more space. There's more repulsion between them, right? This is repulsion and repulsion. This is the first concept that is talking about the repulsion as compared to the, now this repulsion is going to be comparison, having a comparison between the lone pair and the bonded pair, and you can see the two-headed arrow is representing the pairs of electrons and the repulsion actually between them, okay. So we have this pairing. So the repulsion is lone and lone repulsion, lone pair versus lone pair, repulsion, more repulsion, and as compared to the bonded pairs are having less repulsion, okay. So when we are writing an element or the structure of a molecule, so what are we looking for? We are looking for the structures of the molecules actually, okay. Now, and what kind of structures? We are looking for 3D structures, right? So these 3D structures are playing a very important role understanding the geometry. We call it geometry of molecules. So what are we studying? We are studying the geometry of molecules actually. My ideal structure is CH4 methane, okay? And on the basis of this structure, I'll be explaining different other structures. So the basic name of the structure is tetrahedral, okay? And the bond angle is 109.5 degrees, right? So let me draw the structure for you so that you can understand it clearly. So it is AX4, the structure, where A is for carbon and X is for the hydrogen. So let me draw this structure here. So C is exactly here in the center, and we have one of the hydrogen, second hydrogen, third and fourth hydrogen, right? So this is the 3D geometry of this tetrahedral structure actually, right? And the bond angle is here, which is 109.5 degrees. So this structure is my ideal structure, okay? Based on this structure, we are going to see what are the other structures looking alike. So let me tell you that the geometry of the molecule, the shape of the molecule is tetrahedral, and there are four pairs of electrons around him, around this particular structure. It's a non-polar structure. The hybridization is sp3 hybridization, and common example SiH4 is also following the same sort of an example. So moving on to, once again, as I told you, this is my ideal structure. On the basis of this structure, I'm going to explain different other structures, okay? So let's move on to, I'll be either adding the removing the pairs of electrons to the structure or adding the pair of electrons to this structure. So let me just start removing the pair of electrons from. So if I remove one of the electron pair from this structure, it will be like I'm not removing the electron pair, but I'm just introducing one lone pair to this structure. So it will become like, just let me draw once again. It will be C with one, structure will be like this, okay, where you're having lone pair and bonded pairs. So lone pairs are now with me 0, 1, and in this structure there is no lone pair, okay? So only we have bonded pairs. And how many bonded pairs are there? 4. And here the bonded pairs are now 3. Now when you see this is lone pair is going to be pushing these two far away from each other, right? So the bond angle, every lone pair, keep that also in mind, that one lone pair is equal to 2.5 degrees of decrease in the bond angle, okay? This is a very interesting point. Decrease in bond angle by 2.5. So the original bond angle, which you can see here, is how much is the original bond angle? It's 109.5. It will be reduced to 109.5 minus 2.5. So you will get 107 degrees, right? And the name of the shape is going to be changed to, shape is now called pyramidal, right? And the bond angle has changed to this. Now, where will you see this in real molecules? So ammonia is one of the example. Common example is ammonia, which is NH3, and it's following the same properties. Okay, so NH3 with number of here, here, and here. The bond angle is this one, which is 107 degrees, right? And the name is pyramidal. Okay, now moving on to, once again, the structure, which is CH4. Now this time I'm going to add something, removing one more pair, which is a bonded one, and adding one lone pair to that. So the carbon is still there, right? Hydrogen and the hydrogens are there. So two of the pairs are here once again. This time 2 times 2.5 degrees of change will be there, which is equal to 5 degrees, right? So the original shape of CH4, which was 109.5 degrees, and now this CH2 is having a decrease of 5 degrees, so we are going to subtract that 5 from here. You will get 104.5 degrees. Now the shape is, this shape will be called V shape, right? And the bond angle is changed to 104.5 degrees. And the common example that we follow is the example of water. So this is the example of the molecule which I'm going to give you right now. It is H2O. Now if you see oxygen in the center, 1 pair, second pair, 2 pairs are there, right? So this bond angle is 104.5 degrees, right? So this is one of the amazing structure of water, which is V-shaped. Okay, this is V-shaped structure. That was just by removal of one electron or another electronic pair. Moving on to one more shape. Now I'm going to be removing the electronic pair, and I'm not going to use any other pair there. So you can see here once again CH4 is my ideal structure, where bonded pairs are 4, and there is no lone pair. So what I'm going to do this time is I'm going to remove bonded pair 1, and I'm not going to use any lone pair there. So it will become something like this if I remove one of the bonded pairs. So how many bonded pairs are left here with me? Bonded pairs are now with me 3, and lone pair is 0. So the bond angle will goes to 120 degrees, okay, and it's called the structure name is, it's trigonal planar, okay. So bond angle is 120 degree and it's trigonal planar structure. Okay, where can you see the real example? The real example, you will see it in the molecule of BF3 boron trifluoride, where boron is exactly in the center. You have 1 and 3 of the fluorides around it. Okay, so it's 120 degrees. It's called boron trifluoride, and it's a TP structure. I call it TP, or trigonal planar structure. Now I'm going to introduce extra pairs of electrons to the structure, to the methane. It was CH4, my ideal structure with me, and bonded pairs, which I'll be showing with BP, are 4, and lone pair is 0 here. Now I'm changing this to another shape of molecule, and I used to call it AX4 structure, okay. And now I'm going to introduce the AX4 structure, another pair of shared pair of electron range. So it will become AX5 structure, which is PCl5 structure. So how to draw this structure? I want you to focus here. P is in the center, okay, and now 1, 2, 3, 4, and 5, okay. So it's called trigonal base bipyramidal structure. This is the trigonal base. It's called trigonal base bipyramidal structure. Okay, so the original structure is going to be moving into these are the two pyramids which are being made. So this is the structure, and the bond angle goes to, this bond angle is 120 degrees, and the other bond angle, which is the vertical one, is 90 degrees, right? So it's trigonal bipyramidal structure, and it's a very, very important one. Bipyramidal, pardon me for that. It's a bipyramidal shape actually. So it's like P 1, 2, 3, 4, 5, right? This is Cl, 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 and Cl. This is called trigonal based bipyramidal shape. Moving from trigonal based bipyramidal shape, we have an introduction of another pair to it, which is SF6. Now this shape, S is in the center. You have a square based bipyramidal shape 1, 2, 3, and 4. It's called square based bipyramidal shape. Square based bipyramidal, which is having, okay, this is called square based bipyramidal shape. And the bond angle is always 90. There is no other bond angle. So it's called square base bipyramidal shape. Okay. Now the last structure that we people study is IF7, right? In IF7 structure, we have iodine exactly in the center. It is AX7 structure, okay? So it's having a pentagonal base or pentagonal base. This is the base, and I, 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 and I, right? It's called pentagonal base bipyramidal shape. Pentagonal base bipyramidal. Okay, so bond angle, if I divide 360 by 5, so this bond angle is 72 degrees, okay, and the vertical one is 90 degree. So the bond angles are also clear, 90 and 72 degrees. This is called pentagonal base bipyramidal shape. Now these are like crystal structures, okay? So if I'm going to redraw this structure for you, just see this, how will it look like? So iodine is exactly in the center, IF7, and if I just show 1, 2, 3, 4, 5, 6, 7, and the fluorine, let me show it. IF is for the fluorine. How would it look like? I'm just going to show this, draw this for you. So this is a pyramid number 1, okay, right? This is the base of the pyramid, right? And this is placed on a mirror, like you place it on a mirror and you see, and how will it be looking like? So this one, see this? This is a double mirror sort of structure, right? So this will be called IF7, and it's basically pentagonal base bipyramidal, and it is a shape which is quite clear right now. So watch the channel, keep watching it. Thank you very much. I've taken a lot of your time. Thanks a lot. Revise it and do contact me please if you find any kind of problem there. Thank you.